A single particle crosses a room in the dark. No one watches, no instrument measures, and according to the most tested theory in the history of science, it has no position, no path, and no definite existence until someone decides to look. Scientists built an experiment where that choice, to look or not, was made after the particle had already arrived. The results suggested the particle reached back through time and rearranged its own history. Then they built another, and another. Each result was more disturbing than the last. We are going to walk through these experiments, one by one, what they showed, what they proved, and what they broke. If you enjoy what you find, subscribe and stay close. Something stranger is always ahead. Picture a wall with two small holes cut into it. On one side of the wall, a device fires particles toward those holes, one at a time, each alone, separated from the next by seconds of silence. On the other side, a detector screen waits to record whatever comes through. The particles are electrons, each one so small that 1 billion of them could rest inside the period at the end of this sentence without crowding. The setup looks insultingly simple. Two holes, a stream of particles, a screen. You would expect two bands of impact marks, one behind each hole. That is what every intuition about physical objects predicts. That is what paint does when you spray it through two gaps. That is what anything does when it passes through one of two openings. What the screen actually shows is nothing like that. Instead of two bands, the electrons assemble a pattern of alternating bright and dark stripes, dozens of them, spreading across the entire screen, appearing even in regions with no direct line of sight to either hole. This is an interference pattern, the rippling structure that forms when two sets of waves collide in water. When crests reinforce crests and troughs cancel each other out, two waves do that. One particle, alone in the dark, should not be able to do that at all. Scientists assumed the pattern had to be a collective effect, something emerging from many electrons pushing each other around. So they slowed down the gun, 1 electron per second, 1 per minute. Each particle fired alone into the dark, long after the previous one had already hit the screen, with no possibility of interaction. The interference pattern kept building, shot by shot, over thousands of individual particles, the same rippling bands assembling slowly on the screen. Each electron, alone and unobserved, traveled through both holes simultaneously. It spread out as a wave of probability, took two paths at once, and interfered with its own two paths before collapsing to a single point. The superposition was not ignorance about the path. It was the actual physical state of the electron. The interference pattern is direct evidence of this. A particle that took only one path would produce one band. The interference pattern proves something took both paths. That something was a single particle. The interference phenomenon occurs because the electron's wave function, the mathematical description of its quantum state, evolves according to the Schrödinger equation during flight. That equation is linear, which means a wave function that is a sum of two solutions is itself a valid solution. The electron that started at the source has a wave function that is a sum of the wave function for going through hole 1 and the wave function for going through hole 2. Both components are real. Both arrive at the screen. Both contribute to the probability of impact at every location on the screen. The bright stripes correspond to locations where the two components arrive in phase and reinforce. The dark stripes correspond to locations where they arrive out of phase and cancel. The electron always lands somewhere bright, never somewhere dark, because the dark regions have zero probability. The wave function has calculated exactly where the electron can and cannot land, and it has done so using both paths simultaneously. What confirmed the wave interpretation so thoroughly was a simple variation. Scientists fired one electron at a time, so slowly that each electron hit the screen and was recorded before the next was even emitted. No electron ever shared space with another. If the interference arose from multiple electrons interacting, it should have disappeared. Instead, it persisted, shot by shot, the same pattern assembling itself from a long series of individual impacts, each one apparently random, but collectively building something that demanded a global explanation. The pattern requires every electron to have been influenced by both holes simultaneously. The only available explanation is that each electron existed during its flight as a spread-out wave of probability that passed through both openings. The wave interfered with itself. Then, at the moment of detection, the wave collapsed and the electron appeared as a point. This collapse is the first great mystery. The wave function, the mathematical object describing the electron's state, evolved according to a perfectly smooth, deterministic equation during flight. But at the moment of detection, it snapped abruptly into a point. The equation governing the flight does not produce this snap. Something additional must happen. Something that quantum mechanics describes in terms of measurement, but does not explain in terms of mechanism. This unexplained transition from wave to particle, from spread-out probability to definite position, is called the measurement problem. It has been with quantum mechanics from the beginning and has never been solved. What every physicist agrees on is the result. A single electron, fired alone, produces a contribution to an interference pattern that can only exist if the electron went through both holes. The experiment has been repeated with neutrons, with atoms, with increasingly large molecules. In 1999, a team in Vienna used Buckminster fullerene, a 60-atom carbon sphere. In 2019, the same principle was demonstrated with molecules containing over 800 atoms. The quantum behavior does not stop at small scales. It extends upward into objects that would be visible under a powerful enough microscope. The boundary between quantum and classical is not where anyone expected it to be, and it becomes stranger still when you ask what happens the moment you try to look. The wave-particle duality observed in the double-slit experiment is not peculiar to electrons. Every quantum particle exhibits it. Photons of light show the same interference when sent through two slits, one at a time. Neutrons do too. The interference pattern with neutrons was first demonstrated in 1974 by Helmut Rausch and colleagues in Vienna, using crystal lattice planes as the diffraction grating instead of machined slits. Cold atoms show the same effect. The universality of wave-particle duality means it is not an accident of the electron's specific properties. It is a feature of quantum mechanics itself, a property of any quantum system, arising from the linear structure of the Schrödinger equation. Any quantum object, described by a wave function, has the potential to show interference when its possible paths are not distinguished by any record. The constraint is always the same. Which path information must be absent? The quantum world requires ignorance. Physicists tried to catch the electron choosing a slit. They placed detectors at the holes, instruments designed to register which path the electron took, and waited to see what the screen would show. The answer was immediate and unambiguous. The interference pattern vanished. The rippling bands collapsed into two ordinary marks, one behind each hole. The electron stopped behaving like a wave. This seems like it should follow from disturbance. The detector interacted with the electron, nudged it off course, disrupted its delicate quantum state. But the scientists tried gentler and gentler detectors. Instruments so subtle they barely touched the electron. It made no difference. The interference was gone as long as which path information was available, regardless of how gently the measurement was made. The critical variable was not disturbance, it was information. When a record existed anywhere in the experiment, when any detector in any part of the apparatus could in principle have registered which hole the electron used, the interference vanished. When scientists erased the records completely, making the which path information physically unavailable, the interference returned. The universe, at the quantum level, keeps track of what can be known, and it behaves differently based on that tracking. When a fact about the electron's path is accessible, the electron behaves like a classical particle. When that fact is inaccessible, it behaves like a wave. Information is not merely a description of reality, it is a component of it. The physical behavior of matter depends on the information content of the universe. This is what the double-slit experiment actually proves. It is not a demonstration of how small particles are or how tricky they are to measure. It is a demonstration that information has physical consequences. The availability of a record of what happened changes what happened. Carry that thought forward. It becomes important. The observation that information, rather than disturbance, governs quantum behavior was sharpened into a precise theoretical statement by Niels Bohr in his principle of complementarity. Bohr argued that wave-like behavior and particle-like behavior are complementary aspects of quantum objects, never simultaneously observable. When you arrange an experiment to display one aspect, the other is necessarily suppressed. Arrange the double slit to show interference, and you cannot know the path. Arrange it to reveal the path, and the interference disappears. The two aspects are mutually exclusive. The experiment that reveals one necessarily prevents the appearance of the other. This is not a limitation of technology. It is a fundamental feature of quantum reality, built into the structure of quantum mechanics at the mathematical level. The commutation relations between conjugate variables, position and momentum, or time and energy, are the formal expression of this complementarity. The world is structured so that wave and particle properties cannot both be fully defined at the same time. The experiment has been scaled up in ways that should cause you to lose sleep. Buckminster fullerene is a molecule made of 60 carbon atoms arranged in a perfect sphere, sometimes called a buckyball. It is about 1 nanometer across. You could fit 1 billion of them inside a human red blood cell. But by molecular standards, it is large. It has internal structure, it vibrates, and when it is fired through a double-slit apparatus, it produces an interference pattern. The 1999 Vienna experiment was significant because it pushed the quantum boundary higher than it had ever been pushed before. The buckyball traveled through both slits simultaneously. A structure of 60 atoms, with its own internal chemistry, spread out as a wave of probability and interfered with itself. The result was exactly what quantum mechanics predicted. In 2019, the same team went further. They achieved interference with molecules containing over 800 atoms, molecules complex enough to have their own structural dynamics, flexible and warm. These objects are at the edge of what can be called quantum by intuition, and they showed interference. Every time the scale is pushed higher, quantum behavior persists. This tells you that the classical world, the world of definite objects with definite positions, is not a different kind of world from the quantum one. It is an emergent description of the quantum world, valid at large scales because large objects are constantly entangled with their environments. That entanglement destroys quantum coherence so rapidly that superpositions are practically invisible at human scales. But they are still there. The foundation of everything solid is a sea of probability waves. The question is not whether quantum mechanics governs large objects. It does. The question is why we never see it. And that question connects directly to the measurement problem and to the experiments about time that are coming. The decoherence explanation for why large objects do not show quantum interference is precise and quantitative. For a molecule traveling through a double-slit apparatus, decoherence is caused by collisions with background gas molecules, by absorption and emission of thermal photons, and by any other interaction that could, in principle, carry away which path information. Each such interaction entangles the molecule with an environmental particle. The entanglement between the molecule and the environment effectively records which path the molecule took from the environment's perspective. As more and more environmental particles become entangled with the molecule, the interference between the two paths in the molecule's wave function is suppressed. Quantitatively, the interference fringe visibility falls exponentially with the number of decoherence events. A single decoherent interaction that transfers even 1 bit of which path information to the environment is enough to completely suppress the interference. The precision of this relationship, confirmed in the molecular interference experiments in Vienna, is one of the most beautiful quantitative demonstrations of the information principle in quantum mechanics. John Archibald Wheeler asked a question in 1978 that reframed everything. Wheeler was one of the most important physicists of the 20th century, a man who worked alongside both Einstein and Bohr, who coined the term black hole, who thought harder about foundations than almost anyone. His question was simple in form and monstrous in implication. What happens, he asked, if you delay the choice? What if you wait until the particle has already passed through the holes, and only then decide whether to measure which path it took? Every classical instinct says this should not matter. The particle passed through one hole or the other. Its path is fixed. You are just choosing when to look. The decision you make after the fact reveals what already happened, but it cannot change it. Quantum mechanics says something different. If the particle has no definite path before measurement, if it is genuinely in a superposition of both paths all the way to the detector, then the choice of measurement setting, made at any time before the final measurement, should still determine whether the particle had a definite path. And if you make that choice after the particle has passed the wall, the determination of the path is retroactive. The measurement creates the path that already occurred. Wheeler illustrated this with a cosmic version. A photon emitted by a quasar billions of light years away travels through the universe. Along the way, it passes a galaxy whose gravity bends light, offering two paths around the galaxy. The photon travels both paths as a wave. It has been doing this for billions of years. Then it nears Earth, and an astronomer decides whether to look for interference or to identify the path. The astronomer makes that choice now. The photon has been traveling since before the Earth existed, and yet, according to quantum mechanics, the astronomer's choice today determines retroactively what the photon has been doing for billions of years. Wheeler called this participatory retrospective creation. He was precise, not changing the past, but creating it. The past had no definite content until the present looked. The universe's history is not fixed. It is waiting to be specified. This was a thought experiment in 1978. What happened when physicists built the experiment and ran, it should not be as surprising as it is. Wheeler's thought experiment was more than a puzzle about individual photons. It was about the structure of cosmic history. He argued that the universe is full of information about its own past, encoded in the radiation and particles that have been traveling through space for billions of years. And he argued that the content of that information is being determined continuously by the observations that intelligent beings make of it. Every time a telescope is pointed at a distant quasar, every time a photon is detected that has been traveling since before the Earth formed, the act of detection participates in determining what that photon was doing during its long crossing. The universe's past, in Wheeler's picture, is not a fixed archive stored somewhere in the fabric of space-time. It is a quantum potential that is actualized, detail by detail, by every observation made in the present. The universe is writing its own history, retroactively, through the observations made by the observers it eventually produces. The laboratory version of Wheeler's delayed choice experiment was first built by Carroll Alley and colleagues in the 1980s. The setup used a photon interferometer, a device that splits a photon's path into two and then recombines them. At the recombination point, the photon either shows interference, if it traveled both paths, or shows which path behavior, if one path was blocked. The choice between these two modes was made randomly after the photon had entered the device. The results matched quantum mechanics. When the interferometer was set to show interference appeared. When it was set to reveal the path was revealed. In neither case did the photon seem to have decided anything before the measurement setting was chosen. The definitive version came in 2007 from Vicent Jacques and colleagues in Paris. They used a quantum random number generator to set the measurement mode after the photon had entered the interferometer. The photon was already inside, already in superposition, when the random number generator fired. The choice was made, then the photon arrived. thousands of trials. Not a single deviation. The photon always behaved consistently with the measurement setting that was made after it entered. When interference was demanded, interference appeared. When which path information was demanded, it was there. The photon had no path before the measurement. The measurement created the path retroactively. The Paris experiment is considered definitive in quantum foundations. It did what Wheeler's thought experiment demanded and found exactly what quantum mechanics predicted. The past does not have a fixed story until the present writes one. A choice made now determines what a particle was doing a moment ago in the same device before the choice existed. Scale that up to Wheeler's cosmic version. Use a photon that has been traveling for billions of years. The retroactive determination stretches back to before the Earth formed. The astronomer observing tonight is participating in creating cosmic history that is billions of years old. But even this is not the strangest part. The strangest part is what happens when you erase information that has already been created and find that the past changes to match. The 2007 Jacques experiment used a photon that traveled only a few meters inside a laboratory interferometer. The retroactive path determination extended only a few nanoseconds into the past, but the principle scales. In 2017, Johannes Hansteiner and colleagues at the Institute for Quantum Optics and Quantum Information in Vienna used photons from quasars to generate the random measurement settings in a Bell test. The quasars were over 600 light-years away. Their photons had been traveling for over 600 years. Any hidden variable that needed to correlate with the measurement settings would have needed to have been established over 600 years ago. Bell inequalities were still violated. The quantum correlations persisted even when the freedom of choice loophole was pushed back 600 years. In 2021, the experiment was extended further, using quasars billions of light-years away. The retrocausal structure, if that is the right description, extends to cosmological timescales. The universe's quantum correlations span its entire history. The quantum eraser was proposed by Marlon Scully and Kai Druhl in 1982. It takes the delayed choice concept and adds a new element, more than delaying the measurement of which path information, but physically erasing that information after the particle has already been detected and watching what happens to the data already collected. The setup relies on entanglement. A photon enters a crystal and splits into two entangled photons. The first, called the signal photon, heads toward the main detector screen. The second, called the idler photon, is sent in a different direction to a separate detection system. The idler carries which path information about the signal. As long as that information exists in the idler, the signal photon produces no interference pattern. The which path information has been created, just encoded in a different particle. Now the question, what happens if the idler photon is detected in a way that erases the which path information, not merely leaving it unread, but physically scrambles it, sends it through a beam splitter that combines the two paths and makes it impossible to determine which was which? The which path information is destroyed, utterly gone. When this happens, the signal photon data shows interference correlations, even in the data that was already collected. Think about what this means. The signal photon hit its detector first. Its position was recorded. Then the idler photon reached its detector and had its path information either preserved or erased. The signal photon data, already collected, already in the record, shows or hides interference depending on what happened to the idler photon afterward. The already recorded data was shaped by a future event. The quantum eraser experiment comes in several variants, each designed to test a specific aspect of the principle. The basic eraser uses entangled photon pairs and shows that which path information encoded in the idler destroys interference in the signal, while erasure of that information restores it. A spatial version separates the idler detectors far from the signal detectors, testing whether the distance between eraser and screen matters. It does not. A temporal version, the Kim experiment, separates the signal and idler detections in time, showing that the temporal order does not matter either. Whether the eraser acts before or after the signal detection, whether it is near or far, the result is the same. Erasure restores interference and preservation destroys it. The principle is robust across all the variations. The universe tracks which path information, regardless of where or when it is stored, and it restores quantum behavior as soon as that information is genuinely gone. The 1999 experiment by Yoon Ho Kim and colleagues made this temporal dimension unavoidable. In the Kim setup, the signal photon traveled a short path to the main screen and was detected. The idler photon traveled a much longer path through a carefully designed optical system to 4 different detectors. 2 of those detectors preserved which path information. 2 erased it. The routing to each detector was random, determined by quantum chance at beam splitters, and because the idler path was longer, the signal photon hit the main screen before the idler photon reached any of its detectors. The sequence was signal photon detected, then idler photon detected. When the researchers analyzed the data, they split the signal photon records by which idler detector each signal photon's partner ended up at. The signal photons whose idler partners ended up at erasing detectors showed interference. The signal photons whose idler partners ended up at which path detectors showed no interference. The pattern was determined by the idler photon's fate, which was decided after the signal photon had already hit the screen. Something that had already happened was correlated with, and in some sense determined by, something that happened later. Physicists are careful at this point. The interference in the signal data is invisible without comparing it to the idler data. If you look only at the raw signal photon positions, you see noise. The interference only appears when you subset by which idler detector was triggered. This means you cannot exploit the effect to send information backward in time. The pattern is hidden inside correlations that only emerge when you compare 2 datasets from different times. But the correlations are real. The future measurement on the idler genuinely determines what is hidden in the already collected signal data. The past was shaped by the future. The word for that is retrocausality, and it makes physicists deeply uncomfortable for good reason. The Kim experiment used a specific optical configuration that has become a standard reference for temporal quantum eraser demonstrations. The signal photon followed a short path, about half a meter, from the down conversion crystal to the main detector. The idler photon followed a much longer path, about 3 meters, through a system of beam splitters and mirrors before reaching the secondary detectors. The additional path length delayed the idler's arrival by about 10 nanoseconds relative to the signal. The signal photon hit the screen about 10 nanoseconds before the idler reached its detectors. The already recorded positions of the signal photons were then analyzed in subsets based on which idler detector each partner triggered. The subsets showed interference or no interference in exact correspondence with whether the idler detector preserved or erased the which path information. The 10 nanosecond delay was enough to separate cause and effect in any classical picture of causation. In quantum mechanics, the temporal order made no difference. Entanglement is the thread that connects all of these experiments, and to understand it fully, you need to go back to where it became a proper scientific controversy, Einstein's famous objection. In 1935, Albert Einstein worked with Boris Podolsky and Nathan Rosen to publish a challenge to quantum mechanics. The challenge was not about quantum mechanics being wrong. They accepted that its predictions were correct. Their argument was that quantum mechanics was incomplete, that it was missing something, and that something was what they called hidden variables. Their argument rested on entanglement. 2 particles interact and fly apart. Measuring one instantly determines the state of the other, regardless of distance. Einstein found this implication intolerable. If measuring one particle instantly affects the other, either there is hidden information carried by both particles from the start, telling each what result to give, or some influence is traveling between them faster than light. Einstein dismissed the second option as incompatible with special relativity and preferred the first. The particles carried preset answers. The correlation was predetermined. He called the alternative spooky action at a distance and spent years trying to prove it was impossible. For 20 years, the argument lived entirely in the territory of thought experiments. Both quantum mechanics and any hidden variable theory predicted the same outcomes on individual measurements. You could not distinguish them by looking at either particle alone. The difference would only appear in the statistical correlations between simultaneous measurements on both particles, and the technology to test those correlations with sufficient precision did not exist. Then, in 1964, John Bell proved that the two pictures were not equivalent. He derived a set of statistical inequalities that any local hidden variable theory must satisfy. Quantum mechanics predicted violations of those inequalities for specific measurement configurations. The predictions were quantitatively different. An experiment could decide. Bell had given physics a test, not a thought experiment, but a real, runnable test with measurable outcomes. Either the correlations obeyed Bell inequalities, confirming hidden variables, or they violated them, confirming quantum mechanics and demolishing every local classical explanation simultaneously. The universe would have to choose sides. The entanglement created in spontaneous parametric down conversion is specifically polarization entanglement. The two daughter photons are produced in a superposition of both having vertical polarization and both having horizontal polarization. This entangled state has the property that measuring the polarization of one photon instantly determines the polarization of the other. If one is found to be vertically polarized, the other will also be found vertically polarized. If one is horizontal, the other will be horizontal. The correlation is perfect, not approximate, regardless of the measurement angle, the distance between the photons, or the time elapsed between the two measurements. This perfect correlation is what makes entangled photons useful for quantum cryptography, quantum teleportation, and the quantum eraser. The correlation exceeds what any classical source of correlated photons could produce, as Bell's theorem proves. It is a genuinely quantum resource, arising from the non-separable structure of the entangled quantum state. The first real Bell test was performed by John Clauser in 1972. He used pairs of entangled photons, measured their polarizations at various angles, and computed the correlations. Bell inequalities were violated. The quantum correlations were stronger than any local hidden variable theory could produce. Quantum mechanics won, but the 1972 experiment had known weaknesses. Detectors were inefficient, catching only a fraction of photon pairs. The measurement settings were not switched rapidly enough to rule out the possibility that the photons had been informed of those settings by a slower-than-light signal during the experiment. These were not fatal objections, but they were openings through which a stubborn defender of classical reality could still escape. Alain Aspect addressed the most critical weakness in 1982. He built a Bell test in Paris, in which the measurement settings on both sides of the apparatus were switched rapidly and randomly after the photons had already left the source. The switching was fast enough that no signal traveling at or below the speed of light could carry the new settings from one end of the apparatus to the other before the measurements were completed. No classical signal could have coordinated the photons with the new settings. The photons were already in flight when the settings were chosen, and Bell inequalities were still violated. The quantum correlations survived the test. Aspect's result was widely regarded as decisive, but science requires exhausting every escape route, however unlikely, because the stakes are so high. The nature of reality itself is on the table. Two loopholes remained. The detection loophole said that inefficient detectors might be sampling a biased subset of particle pairs. The freedom of choice loophole said the random number generators might themselves be correlated with hidden variables. Closing both loopholes simultaneously required building a better experiment. That experiment was built in Delft. Alain Aspect's 1982 experiment was technically demanding in ways that are hard to appreciate from a description. The switching of the measurement settings had to occur faster than the time it took light to travel from one measuring station to the other. The two polarizers were about 13 meters apart, so the switching had to occur in less than about 40 nanoseconds. Aspect's team used acousto-optical switches, which could switch between two orientations in a few nanoseconds using sound waves in a crystal. The settings were not truly random in Aspect's experiment, using a quasi-periodic pattern instead, but the pattern was fast enough and irregular enough to close the locality loophole for practical purposes. Later experiments improved on this, using quantum random number generators and faster switches, eventually arriving at the loophole-free Bell tests of 2015 that used true quantum randomness to set the measurement choices. In 2015, Ronald Hansen's team at Delft University performed the first loophole-free Bell test. They used electron spins trapped in nitrogen vacancy centers in diamond crystals, one on each side of the experiment, separated by 1.3 kilometers. The entanglement between the two spins was established using photons that traveled from each crystal to a middle point and interfered there. Detection efficiencies were high enough to close the detection loophole. The settings were switched fast enough, and the distance was great enough to close the locality loophole. Both closed at once. Bell inequalities were violated. The case was closed. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for establishing the violation of Bell inequalities through experiments with entangled photons. The Nobel Committee described their work as foundational for quantum information science. What they had actually done was prove that the universe is not locally real. Local realism is the conjunction of two assumptions: that nothing influences anything faster than light, and that physical objects have definite properties independent of observation. The Bell experiments proved you cannot have both. One is wrong, maybe both. The quantum world is either non-local, with instant influences spanning any distance, or non-real, with objects having no definite properties until measured, or some combination of the two. Einstein was wrong about hidden variables. He was wrong about spooky action at a distance. The universe is exactly as strange as quantum mechanics says it is. And this result, this demolition of local realism, connects directly back to the double slit and the quantum eraser. The correlations in the Kim experiment, where a future measurement on an idler photon determines the pattern hidden in already collected signal photon data, are a specific case of quantum entanglement correlations. The entangled pair was created together. Their shared quantum state connects them across space and across time. What happens to either particle, whenever it is measured, is constrained by that shared state. The universe allows correlations across time just as easily as correlations across space. The direction of time, as far as the quantum correlations are concerned, is not special, and the next set of experiments digs into exactly what that means for the nature of causality and for the nature of reality itself. The 2022 Nobel Prize announcement described the winning work as experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The committee noted that the work has implications for how we understand the nature of reality and that it has enabled the development of quantum computers, quantum networks, and quantum encryption. But the deepest significance of the work is not its applications. The deepest significance is the verdict it delivered on the structure of physical reality. Local realism, the conjunction of locality and realism, is false. The universe does not consist of classical objects with pre-existing properties at definite locations, connected only by locally propagating influences. Whatever the universe is, it is more deeply interconnected than that. The correlations between entangled particles span any distance, cannot be explained by any classical mechanism, and are verified to the highest precision achieved by any physical measurement. Reality is non-local, or non-real, or some combination that does not yet have a good name. What does it mean for the universe to be non-local? Most people hear that word and imagine signals flying instantly from one place to another, telephone calls across the galaxy, information transmitted without delay. The actual situation is both stranger and more subtle than that. The correlations between entangled particles are real and immediate. When you measure one particle of an entangled pair and find spin up, the other particle is instantly in a state that will give spin down if measured, no matter how far apart they are, no matter how recently the measurement setting was chosen. The correlation is there, immediately, without any delay. But here is the catch. You cannot use this to send information. Measuring your particle gives you a random result. You cannot choose what result you get. Your partner, on the other side of the experiment, also gets a random result. The correlation between your two random results only becomes apparent when you compare notes, which requires a classical communication channel that moves at or below the speed of light. The non-locality is real, but it is sealed behind a veil. The universe allows it. The universe uses it in the sense that quantum mechanics is built on it. But the universe also prevents you from exploiting it for faster-than-light communication. It is as if reality is designed to tease, showing you the scaffolding of something extraordinary and then refusing to let you climb it. This frustrates people who expect the universe to be either classical and mundane or radically different in usable ways. What the Bell results actually show is a universe that violates classical intuitions precisely where those intuitions matter most, at the level of fundamental properties and causal connections, while carefully maintaining the speed of light as a limit on practical information transfer. The correlations are there. They are provable. They cannot be explained by any local hidden variable theory, and they cannot be used to send a message to the past. The universe is strange at the deepest level, but continues to work at the practical level, at least so far. The non-signaling theorem is worth understanding in detail, because it is what makes the Bell violations consistent with special relativity. The correlations between entangled particles are real and immediate, but they cannot be exploited to send information faster than light. The reason is that each particle's measurement outcome is individually random. You cannot choose what result you get when you measure your particle. Your partner, measuring their particle at the same moment on the other side of the world, also gets a random result. Neither of you can tell, from your individual result alone, what the other got. The correlation only becomes apparent when you compare notes. And comparing notes requires sending a classical message which cannot travel faster than light. The non-local correlation is real, but it is locked inside the joint statistics of the two outcomes. You cannot access the joint statistics without a classical communication channel. The universe hides the non-locality just out of reach. The cosmic Bell test of 2017 pushed the experiment to its logical extreme. Johannes Hansteiner and colleagues in Vienna used light from distant quasars to generate the random bits that set the measurement choices in a Bell test. The quasars were over 600 light-years away. Their light had been traveling for over 600 years. The idea was to address the freedom of choice loophole in the most extreme way possible. If hidden variables were determining both the measurement settings and the particle outcomes, those hidden variables would need to have been coordinated over 600 light-years, over 600 years ago, to produce the quantum correlations. Any classical conspiracy to fake the quantum results would need to have been arranged before the first European explorers crossed the Atlantic. Bell inequalities were still violated. The quantum correlations held. The free choice of measurement settings, driven by photons that had been traveling since before European sailors knew the Americas existed, still produced violations that no local hidden variable theory could explain. A year later, the Big Bell test coordinated over 100,000 human volunteers from around the world to provide random bits for measurement settings in Bell tests, running simultaneously in 12 laboratories across 9 countries. Humans played video games, made choices, and those choices set the measurement settings. The freedom of choice loophole was pushed back to the assumption that human choices are genuinely free, which is either philosophically obvious or philosophically problematic, depending on your views about free will. Bell inequalities were violated again. Every time the test is run, with every possible closing of loopholes, the quantum correlations persist. Local realism is gone. But notice what you are accumulating here. You have an experiment showing that information destroys quantum interference. An experiment showing that the choice of whether to measure is made after the particle enters the device and still determines the outcome. An experiment showing that erasing information that already exists restores interference in already collected data. And experiments showing that correlations between particles cannot be explained by any local or predetermined mechanism. Put these together and a picture emerges. The universe is not made of objects at definite locations with definite properties, causally connected by influences that move forward through time. Whatever the universe is made of, it is something more deeply interconnected, more temporally fluid than that picture allows. The classical world is an approximation, valid at human scales, that breaks down when you push on it hard enough. And the experiments that come next push it harder. The Cosmic Bell Test of 2017 was the culmination of a series of experiments designed to push the freedom of choice loophole as far back in time as possible. The freedom of choice loophole says that if the measurement settings and the particle properties were correlated from a common cause in the past, the Bell violations could be explained classically. Any experiment that uses local random number generators to set the measurement choices is vulnerable to this loophole if the random number generators share a common past with the particles. By using photons from distant quasars to generate the random settings, the Hansteiner experiment pushed the common past back 600 years. To exploit the loophole, a classical conspiracy would need to have been arranged before those quasar photons were emitted. The requirement grows more extreme as you use more distant sources. In principle, you could use sources far enough away that any common cause would need to predate the Big Bang, effectively ruling out the loophole entirely. The 2018 Big Bell test was extraordinary for what it implied about the nature of the freedom of choice loophole. The participants were humans. They made choices that felt to them like free choices. They moved a cursor, pressed a button, selected an option. None of them knew they were part of a physics experiment that would determine the fate of local realism. Their choices were as free as choices can be. The fact that their choices still produced Bell inequality violations tells you something. If local hidden variables were real, if there were preset answers in the particles, then those preset answers would have needed to be correlated with the random choices of over 100,000 people who had no idea they were participating. The conspiracy required would be so vast, so precisely engineered, as to be indistinguishable from magic. Physicists call this the conspiratorial universe objection. You could always posit that everything in the universe is secretly coordinated, that the initial conditions of the Big Bang were fine-tuned to produce fake quantum correlations in every Bell test ever run. This is logically possible. It is also the most extravagant and vacuous explanation ever proposed for a physical phenomenon. The scientific conclusion is simpler and more honest. The universe is not locally real. The correlations are genuine. Quantum mechanics is right about something that Einstein spent years trying to deny. And what quantum mechanics is right about includes entanglement across time as well as across space. The quantum eraser showed this. The delayed choice experiment confirmed it. The Bell tests established the framework for understanding it. The nature of time and the direction of causation is not what classical physics assumed. To understand how deep this goes, you need to look at the measurement problem from a different angle. Not the angle of what quantum mechanics says about single particles, but the angle of what it says about observers themselves. The Big Bell test was remarkable for the diversity of its participants as much as for its scale. The 100,000 participants came from virtually every country. They played a variety of games and puzzles that were designed to elicit genuine choices, not reflexive or algorithmic responses. The choices were collected and transmitted in real time to the 12 participating laboratories, where they were processed and used to set measurement angles. The entire process, from human choice to quantum measurement, took place in real time, with no opportunity for the settings to be predicted in advance, based on any prior information. The result? Bell inequality violations in all 12 experiments, running simultaneously with diverse settings generated by diverse participants from diverse backgrounds, is one of the most conclusive demonstrations in the history of physics. The universe does not care how many people are watching or how free their choices are. The quantum correlations persist. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, was the first attempt to say what quantum mechanics actually meant about the world. It said the wave function was not a real physical thing. It was a mathematical tool, a calculator of probabilities. Before measurement, there is no fact about the electron's position. After measurement, there is a fact. The wave function provided the probability distribution. The measurement produced the outcome. Between those two things, there was nothing to explain. This sounds clean, and in many ways, it is clean. It tells physicists to shut up and calculate, to use the tool without asking what it represents. And for practical purposes, this works beautifully. Quantum mechanics, computed using the Copenhagen framework, has produced the most precise predictions in the history of science. The electromagnetic fine structure constant, a fundamental number governing how electrons and photons interact, has been calculated to better than 1 part in 1 trillion and measured to the same precision. The agreement is perfect. But Copenhagen has a deep problem. It places measurement at the center of physics without ever defining what measurement is. Something distinguishes a quantum system from a classical measuring apparatus. Something distinguishes the moment before measurement from the moment after. Something causes the wave function to update, but Copenhagen gives no mechanism for any of this. It simply says it happens. Bohr's response to questions about the mechanism was to say the questions were meaningless. The goal of physics was not to describe what reality is between measurements, but to predict what measurements will find. Asking what the electron was doing before you measured it is like asking what the color of the number 3 is. The question is grammatically formed but scientifically empty. Many physicists found this deeply unsatisfying. It felt less like a solution and more like an instruction to stop asking. The Copenhagen interpretation's strength is its operational clarity. It tells you exactly how to calculate, specify the quantum state, apply the appropriate operators, compute the probabilities. It never tells you anything that cannot in principle be measured. It is a philosophy of measurement outcomes, not of underlying reality. This made it extremely productive for doing physics. Physicists trained in the Copenhagen tradition calculate correctly and design experiments correctly. The theory works in the sense that matters for practice. The weakness is that it purchases this clarity by refusing to describe anything that cannot be measured. It makes physics deliberately incomplete as an account of reality. When a quantum physicist asks what the electron is doing between measurements and is told the question is meaningless, they are being told to accept a theory that does not describe the world, only observations of the world. Many physicists find this acceptable. The goal of physics, they would say, is to predict observations, not to describe a reality behind the observations. Others find it a betrayal of what physics is supposed to be doing. Hugh Everett thought differently. In 1957, as a graduate student at Princeton, Everett submitted a doctoral thesis proposing what he called the relative state formulation of quantum mechanics. It is now called the many worlds interpretation. The core idea was radical and, once grasped, oddly clean. The wave function never collapses. It never has, and it never will. The Schrödinger equation, which describes how the wave function evolves, is always right and always applies. Every quantum interaction, every measurement, every interaction between a particle and a detector causes the universe to branch. Both outcomes occur. In one branch of the universe, the detector fires. In another branch, it does not. In one branch, you see spin up. In another branch, you see spin down. There are no collapses because there is nothing to collapse. The wave function of the universe evolves smoothly and continuously. What we experience as a definite measurement outcome is simply our branch of the universe, one of many, all equally real. Every quantum event that has ever occurred has split the universe into branches. There are incomprehensibly many versions of you, each observing different sequences of outcomes, all of them equally real. The measurement problem is dissolved rather than solved. There is no collapse. There is no special role for observers. There is just the wave function, branching indefinitely, and observers who find themselves in one branch without any access to the others. The appeal is that it takes quantum mechanics completely seriously. It says the Schrödinger equation is always right, without exception, and follows the implications wherever they lead. The cost is an ontology of staggering extravagance. An infinite number of parallel universes, branching with every quantum event, each one as real as this one. And there is a problem with probability. In a universe where every outcome occurs, what does it mean to say one outcome is more probable than another? Probability requires outcomes that might not occur. If all outcomes occur, probability seems to lose its meaning. Various solutions have been proposed, involving the relative sizes of different branches, but the debate continues. The many worlds interpretation has attracted a growing number of adherents since the 1970s. When David Deutsch and others began developing it more formally, Deutsch, who is also one of the pioneers of quantum computing, has argued that many worlds is the only interpretation that makes the computational power of quantum computers comprehensible. A quantum computer with 100 qubits processes all 1,000 billion possible states of those qubits simultaneously. What is doing the processing? Deutsch asks. If only one branch of the wave function is real, there is only one computer, and it can only be in one state at a time. The only way to account for the parallel processing is if all the branches are real and all the processing is happening simultaneously across all of them. Many worlds, in this view, is a consequence of taking quantum computation seriously, arrived at not by preference but by following the physics. David Bohm took a completely different approach. Bohm, working in the 1950s following de Broglie's earlier work, proposed that particles have definite positions at all times. There is no superposition of paths. The electron does not go through both holes. It goes through one hole, but it is guided by a real physical wave, the pilot wave, that does go through both holes and interferes with itself. The pilot wave is real but undetectable directly. It fills all of space, continuously, guiding every particle through its long crossing. When a particle approaches the double slit, its pilot wave passes through both holes and forms an interference pattern on the other side. The particle, following the pilot wave's guidance, tends to land in the bright regions of that pattern and avoid the dark regions. The interference pattern on the screen is a map of the pilot wave, not of the particle's probability. This restores classical realism in one sense. The electron always has a definite position and takes a definite path. Measurement reveals that path rather than creating it. There are no superpositions, no collapses, no parallel universes. The randomness of quantum mechanics is just ignorance about the exact position of the particle within the pilot wave. The cost is non-locality. The pilot wave is a global object. When an entangled partner particle is measured, the pilot wave of the first particle instantly adjusts, regardless of distance. The adjustment is not a signal, because it is not controllable, but it is real, and it is instantaneous. Bohm's theory explicitly violates the spirit of special relativity, even though it can be made consistent with the letter of it. Most physicists find pilot wave theory technically sound but physically unnatural. The pilot wave does its job but never shows up in any other context. It guides particles but can never be directly observed. It is the most successful hidden variable theory that Bell's theorem does not rule out, precisely because it is explicitly non-local. But it is a minority view. The mainstream has never settled on any single interpretation, and the debates that were already old in 1957 are still alive today. The pilot wave theory has a specific and precise prediction about the double-slit experiment that differs from the intuitive picture of a single particle going through one hole. In pilot wave theory, the particle does go through one hole, but the pilot wave goes through both holes and interferes. The interference pattern in the pilot wave guides the particle to land in bright regions. If you could track the particle's exact position throughout, you would find a definite trajectory, deterministic and classical in form, weaving between the two holes and ending up in the interference pattern. The trajectory is not random at all. It is determined by the initial position of the particle, which is unknown to the experimenter but definite in the theory. The statistical distribution of landing positions, averaged over many particles with different initial positions, matches the quantum probability distribution. The randomness is apparent, not real. The determinism is hidden by our ignorance. Carlo Rovelli proposed a different solution entirely in 1996. Relational quantum mechanics takes the perspectival nature of quantum states seriously and turns it into a foundational principle. In ordinary quantum mechanics, the wave function is meant to describe the state of a system, but the wave function changes when you make a measurement. Different observers making measurements at different times get different updates. This seems to imply that the wave function is not describing objective reality, because objective reality would look the same to all observers. Rovelli's proposal is that the wave function is never objective, it is always relational. The state of a quantum system is the state of that system relative to a particular observer or measuring device. There is no absolute observer-independent quantum state. Two observers may have incompatible but equally valid descriptions of the same quantum event. This makes quantum mechanics look more like special relativity. In special relativity, two observers moving at different velocities disagree about the length of an object or the duration of an event. There is no absolute length or duration. Both descriptions are correct relative to each observer's reference frame. Rovelli proposes that quantum states work the same way. Both descriptions are correct relative to each observer. The measurement problem dissolves in relational quantum mechanics, but it does not go away cleanly. It is replaced by the question of why different observers' descriptions remain mutually consistent. Why, when two observers compare notes, they agree on whether an experiment was done, even if they disagree about when the wave function updated. Rovelli has answers, but the debate continues. Relational quantum mechanics has attracted serious attention partly because of its connection to Rovelli's other work on quantum gravity, where the absence of an absolute space-time background makes a relational approach to quantum mechanics seem natural. If space and time are themselves relational, perhaps quantum states should be too. Relational quantum mechanics connects naturally to Carlo Rovelli's other major work in theoretical physics, loop quantum gravity. In loop quantum gravity, space and time themselves are quantized, built out of discrete quantum chunks rather than forming a continuous background. There is no fixed space-time arena within which quantum events occur. Space-time itself is one of the quantum objects, subject to superposition and measurement and relational description. In such a framework, it is natural that quantum states would also be relational rather than objective. If space and time are not absolute, but are defined by the relationships between physical objects, then quantum states, which describe the properties of physical objects, should also be defined by the relationships between those objects. Relational quantum mechanics and loop quantum gravity share a philosophical starting point. There is no view from outside. There is no absolute background. All physical descriptions are internal to the physical world, expressed in terms of the relationships between parts of that world. Yakir Aharonov and colleagues developed a framework called the two-state vector formalism. that takes time symmetry seriously in a way most interpretations do not. The idea is precise and disturbing. A quantum system state is not fully specified by its past preparation alone. The full specification requires both the initial state and the final state, the preparation and the post-selection. In ordinary quantum mechanics, you prepare a system in a known state and then measure it. The measurement gives a result according to the probability distribution the wave function predicts. In the two-state vector formalism, that measurement is only part of the description. The full description requires also knowing how the system will be post-selected in the future, what measurement will be made, and what result will be obtained. Given both pieces of information, the quantum state of the system at any moment between preparation and post-selection is described by two vectors, one propagating forward from the past, one propagating backward from the future. This is a rigorous mathematical framework, not a loose metaphor. It makes the same predictions as ordinary quantum mechanics for any situation where you know only the past boundary condition. The difference appears when you know both boundary conditions, and then it produces what Aharonov calls anomalous weak values. Weak values come from weak measurements, probes of quantum systems gentle enough not to fully collapse the wave function. Standard measurements disturb the system and give one definite result. Weak measurements disturb the system very little and give a blurry result, slightly informative, that you average over many trials to extract meaningful information. When weak measurements are sandwiched between a specific preparation and a specific post-selection, the results sometimes lie outside the range that any ordinary measurement could produce. A spin 1/2 particle normally gives spin values of either +1/2 or -1/2. A weak measurement of a carefully post-selected spin particle can give a weak value of 100 or -47, or a complex number. These anomalous weak values are not errors or noise. They are predicted by the two-state vector formalism and confirmed by experiment. The anomalous weak values predicted by the two-state vector formalism have a striking interpretation. They suggest that the quantum system being weakly measured is not in a definite state at the time of the measurement. Instead, it is in a state that depends on both where it came from and where it is going. The weak value is a sort of average over the contributions from both temporal boundaries, weighted by how close the final state is to each possible intermediate state. When the final state is very close to an eigenstate of the measured observable that is very different from the prepared state, the weak value can be large and anomalous. The anomaly reflects the interference between the forward propagating wave from the past preparation and the backward propagating wave from the future post-selection. Aharonov has described these anomalous values as making visible a kind of quantum presence that the particle has at intermediate times, a presence shaped by both its history and its destiny simultaneously. The anomalous weak values have been demonstrated in multiple experimental systems. In 2011, a team measured the average trajectories of photons in a double-slit experiment using weak measurements, tracing out paths that looked eerily like the classical paths through each slit, even though quantum mechanics says no definite path exists. The image was visually striking and technically careful. The anomalous values, when they appear, are consistent with the two-state vector picture. The particle in the present is influenced by both its past preparation and its future post-selection. The future measurement reaches back and contributes to the result of the present measurement. Not overtly, not in a way that allows faster-than-light communication, but in a way that is mathematically real and experimentally confirmed. This is retrocausality in a controlled, measurable form. It is not sending information backward in time. It is a demonstration that quantum systems are influenced by both temporal boundaries, past and future, not the past alone. The implications are profound. If the quantum state of a system depends on its future as well as its past, then the idea of a quantum system evolving purely forward from initial conditions is incomplete. The future is always there, in the mathematics, always contributing. We usually ignore it because we do not know what the future holds. But in post-selected experiments, where we do know the future, that contribution becomes visible. Aharonov argues that the usual formulation of quantum mechanics artificially breaks time symmetry by conditioning only on the past. A fully time-symmetric formulation would condition on both past and future, and the anomalous weak values are a glimpse of what that fuller formulation reveals. The quantum eraser now looks different in this light. The correlations between past signal photon detections and future idler photon measurements are not statistical coincidences. They are expressions of the time-symmetric nature of quantum mechanics. The entangled pair was created with a quantum state that connects both temporal boundaries. The measurements at both ends are aspects of a single, timeless quantum correlation. Weak measurement has found practical applications beyond testing the foundations of quantum mechanics. In quantum state tomography, the complete reconstruction of an unknown quantum state from measurements. Weak measurements can be used to extract information about the state without fully collapsing it, allowing more information to be gathered from each copy of the state before it is destroyed. In quantum metrology, the measurement of physical quantities with quantum precision, weak values can amplify tiny signals to measurable size. If the weak value of an observable is very large, the deflection of a measuring device can be amplified far beyond its ordinary scale, allowing the detection of extremely small effects. This technique, called weak value amplification, has been used to measure tiny beam deflections, small phase shifts, and other minute physical quantities with higher sensitivity than ordinary measurement methods. The strange mathematics of anomalous weak values turns out to be a precision tool. The quantum Zeno effect provides another window into the relationship between observation and physical reality. George Sudarshan and Baidyanath Misra predicted in 1977 that a quantum system subjected to continuous observation could be frozen in its initial state indefinitely. The prediction was based on the mathematics of repeated measurements and their effect on wave function evolution. It was confirmed experimentally in 1989 using trapped ions and has since been demonstrated in cold atoms, photons, superconducting qubits, and other systems. The basic mechanism is this. A quantum system starts in a state and, left alone, will gradually evolve toward other states. If you measure it, you collapse the wave function back to a definite state. If you measure it very quickly after the initial measurement, the system has had very little time to evolve, so the probability of finding it in the initial state is very high. Measure it again quickly, and again you reset it to the initial state. If you keep measuring faster than the system can evolve, you prevent any evolution from occurring. Continuous observation freezes quantum change. This is physically bizarre. Observation, in classical physics, is a passive act. You watch something happen. The watching does not change what happens. In quantum mechanics, observation is an active intervention. The act of gaining information resets the quantum state. Watch a radioactive nucleus fast enough and often enough, and it cannot decay. The quantum Zeno effect has been proposed as a tool for quantum computation as a way of maintaining coherence in qubit systems by carefully managing observation. It has been realized in experiments. It works. The technology is real, and it sharpens the principle established by the double-slit experiment. Information acquisition is not a passive recording of pre-existing facts. It is a physical act with physical consequences. The universe changes when observed. Observation freezes what would otherwise evolve. This is not a quirk of the measurement apparatus. It is a feature of quantum mechanics itself. The quantum Zeno effect has a counterpart called the quantum anti-Zeno effect. Under certain conditions, frequent measurement can actually accelerate quantum transitions rather than preventing them. Whether the Zeno or anti-Zeno effect dominates depends on the spectral properties of the coupling between the quantum system and its environment, and on the measurement interval relative to the timescales of the system's dynamics. In some systems, a measurement interval that would normally produce the Zeno effect produces the anti-Zeno effect if the system is near a spectral resonance. The competition between the two effects has been observed experimentally in cold atom systems and photonic platforms. The full picture of measurement-induced dynamics in quantum systems is richer than either effect alone suggests. Measurement is not simply a tool for freezing or accelerating quantum evolution. It is an active participant in quantum dynamics, shaping the trajectory of quantum states in ways that depend sensitively on the timing and nature of the measurements. There is a thought experiment that philosophers and physicists have been arguing about since 1961, when Eugene Wigner first described it. Wigner's friend is a version of the Schrödinger's cat problem, but it introduces a second observer and asks whether two observers can have incompatible descriptions of when a wave function collapsed. Wigner imagines a friend sealed in a laboratory performing a quantum measurement. The friend measures the spin of a particle and sees a definite result, either up or down. From the friend's perspective, the wave function collapsed at the moment of measurement. The friend has a definite outcome, but from Wigner's perspective, standing outside the sealed laboratory, the friend and the particle and everything in the lab are a quantum system. Wigner has not made any measurement. From his perspective, the wave function of the combined system, friend plus particle, has not collapsed. The friend is in a superposition of having seen spin up and having seen spin down. Two observers have incompatible accounts of whether the wave function has collapsed. Both accounts are, according to their respective frameworks, correct. This is no longer a thought experiment. In 2020, a team published results from a quantum computation version of Wigner's friend experiment using photonic qubits as the friend's measurement device. The results were consistent with the prediction that both descriptions are simultaneously valid from their respective perspectives, and that there is no observer-independent fact about when the wave function collapsed. Relational quantum mechanics predicted this. The two-state vector formalism accommodates it. Copenhagen sidesteps it by placing the classical quantum divide at the boundary of what counts as an observer, but never saying where that boundary is. Many worlds says both outcomes occurred in different branches, and both Wigner and the friend are right from their respective branches. The measurement problem is not solved. It is not even close to solved. A century of trying has produced multiple internally consistent interpretations and no experimental way to distinguish between them. The question of what happens when you make a quantum measurement, what it means for the wave function to collapse, what an observer actually is, remains as open as it was in 1927. And this openness is significant, not because it means quantum mechanics is wrong. It means physics has reached a frontier where the questions are about the nature of reality itself, and the tools of experimental science have not yet been sharpened enough to answer them. The Wigner's friend problem has been generalized in recent years to create what are called extended Wigner's friend scenarios, in which two separated observers each have their own enclosed laboratory and their own quantum measurement. The two observers are then treated as quantum systems by two outside observers, creating a four-agent scenario. In this setup, it is possible to derive logical contradictions between the different agents' descriptions of the same sequence of quantum events. One agent concludes that a certain event occurred, another agent concludes it did not. A third agent concludes both. Standard quantum mechanics, applied to different observers with different amounts of information, produces these contradictions. The resolution depends on which interpretation you use. Copenhagen says some of the agents' questions are meaningless. Many worlds says all the agents are in different branches and there is no contradiction within any single branch. Relational quantum mechanics says the descriptions are all valid relative to their respective observers and there is no requirement of global consistency. The paradox exists because we keep trying to impose a global, observer-independent description on a quantum world that may not have one. The arrow of time is one of the most obvious features of experience. Events happen in a sequence. Causes precede effects. Memories are of the past, not the future. Hot coffee cools. Eggs break. People age. The sense that time flows in one direction is so built into consciousness that questioning it seems absurd, and yet the fundamental laws of physics do not have a preferred direction of time. Newton's laws of motion, Maxwell's equations for electromagnetism, Einstein's general relativity, and quantum mechanics all have exactly the same mathematical form whether time runs forward or backward. If you filmed a collision between two billiard balls and played the film backward, you could not tell from the physics alone which version was forward. The laws are time-symmetric. The one exception is a subtle asymmetry in certain types of radioactive decay involving neutral kaons. This violation of time reversal symmetry is real but tiny and specific. It cannot explain why cold coffee never spontaneously heats up, why shattered glasses never reassemble themselves, why every process in everyday life runs overwhelmingly in one direction. The explanation for the arrow of time comes not from fundamental physics, but from statistical mechanics. The second law of thermodynamics says that the total entropy of a closed system increases over time. Entropy is a measure of how many microscopic configurations are consistent with the macroscopic state of a system. A broken egg corresponds to vastly more microscopic configurations than a whole egg. The system is overwhelmingly more likely to be in a high entropy state than a low entropy one. So, things naturally evolve from ordered to disordered. But this is a statistical asymmetry, not a fundamental one. The laws of physics would permit coffee to spontaneously heat up. It simply never happens because the probability is incomprehensibly small, not zero, vanishingly small. The directionality of time is a consequence of the initial conditions of the universe, which started in a highly ordered, low-entropy state, not of any fundamental time asymmetric law. This matters for quantum mechanics. If time has no preferred direction at the fundamental level, then quantum mechanics should work equally well with influences running backward as forward, and several physicists have taken this seriously. The time symmetry of the fundamental laws has been tested experimentally in particle physics. The operation of time reversal in quantum field theory is combined with two other symmetry operations, charge conjugation and parity inversion, to form a combined symmetry called CPT. This combined symmetry is believed to be exact, and its exactness has been confirmed to very high precision in the standard model of particle physics. But the individual symmetries can be violated. Parity violation was discovered in the 1950s. CP violation was discovered in the 1960s in kaon decays, and has since been found in B meson decays as well. By the CPT theorem, CP violation implies T violation, a genuine asymmetry under time reversal. This T violation is small and confined to specific particle interactions. It cannot explain the macroscopic arrow of time, but it shows that time reversal symmetry, while approximately true, is not exact in the laws of particle physics. The arrow of time has a tiny fundamental root, alongside the much larger statistical root from entropy. John Cramer proposed the transactional interpretation of quantum mechanics in 1986, building on earlier work in electrodynamics by John Wheeler and Richard Feynman. In Cramer's framework, a quantum event is not a single wave propagating forward from source to detector. It is a transaction between the source and the absorber, involving waves traveling in both directions. The emitter sends out a retarded wave, traveling forward in time, as in ordinary quantum mechanics, but it also sends out an advanced wave, traveling backward in time, into the past. The absorber in the future responds similarly, sending both a retarded wave forward and an advanced wave backward. The transaction is completed when the retarded wave from the emitter and the advanced wave from the absorber reach a mutual agreement, forming a standing wave that exists at all times along the path of the particle. In this picture, the quantum eraser result is natural. The future absorber is always part of the transaction. The signal photon traveling to the screen and the idler photon traveling to its detector are both part of a single transaction that spans the entire experiment. The backward wave from the future idler detector reaches back to the moment of pair creation. The pattern in the signal data reflects the outcome of the full transaction, which includes both boundaries, Kramer's interpretation is not mainstream. Advanced waves traveling backward in time are not generally accepted as physical entities. But the interpretation is mathematically rigorous, consistent with all experimental results, and provides an intuitive explanation for phenomena that are mysterious in other frameworks. Whether it is physically real or merely a useful formalism is an open question. What it points to is significant. A rigorous mathematical framework exists in which the future plays a causal role. The universe does not have to be time asymmetric in its fundamental physics. It chooses to appear time asymmetric at macroscopic scales because of entropy, but the underlying quantum mechanics is perfectly compatible with the future influencing the past. The transactional interpretation has been extended and clarified by Ruth Kastner, a philosopher of physics who has developed what she calls the possibilist transactional interpretation. In Kastner's version, the retarded and advanced waves that form a transaction are not waves in ordinary space-time. They are waves in a space of quantum possibilities, a larger mathematical space that contains all the possible quantum events, as well as the actual space-time events, the possible quantum events that could occur. The transaction, when it occurs, is the process by which a quantum possibility becomes an actual space-time event. This addresses one of the main objections to Kramer's original formulation, which was that advanced waves traveling backward in time through ordinary space-time would be in tension with the causal structure of relativity. In Kastner's version, the advanced waves are in possibility space, not space-time, and no conflict with relativity arises. The transaction is a collapse from possibility to actuality, happening outside of ordinary time and space. The block universe concept from general relativity provides another way to think about time that dissolves some of the paradoxes from quantum mechanics. Einstein's special relativity showed that different observers moving at different velocities disagree about whether two events are simultaneous. There is no absolute present, no universal now that all observers share. What is in the past for one observer may be in the present for another, or even in the future. This leads to the concept of space-time, a four-dimensional structure in which events are points, and the distinction between past, present, and future depends on the observer. Some physicists, particularly those influenced by the philosophy of Hermann Weyl and more recently by Julian Barber, argue that this description implies all events are equally real. The past did not disappear. The future is not yet to come. All of space-time exists at once as a four-dimensional block. The apparent flow of time is something that happens in consciousness, not in physics. We experience time as flowing because we are processes in the block, not because the block is changing. In the block universe, there is no fact about which moment is the present. Every moment is equally real. The 2019 measurement you made exists. The 1999 Kim experiment exists. The first electron ever fired through a double slit exists. All of them equally, simultaneously, as events in a four-dimensional structure. If the block universe is right, the quantum eraser is not changing the past. Nothing changes in a block universe. The correlations between past signal photon detections and future idler measurements are simply features of the four-dimensional structure, relationships between space-time events that happen to involve a time-like separation. The word retroactive implies something changed. In a block universe, nothing changes. The correlations were always there. This is either more or less disturbing than retrocausality, depending on what you find disturbing. The retrocausal picture implies the future is reaching back and actively reshaping the past. The block universe picture implies the past and future were always fixed together in a single structure, and what we experience as causation is just the direction of our temporal perspective through that structure. The block universe picture has been articulated most forcefully by the physicist and philosopher Hugh Price, who has argued that the quantum correlations between entangled particles, including the temporal quantum eraser correlations, are most naturally understood as block universe correlations. rather than as causal influences in either temporal direction. In a block universe, a correlation between two events is just a structural feature of the four-dimensional whole. It does not require any causal arrow. The events are correlated because the block is structured that way, not because one caused the other. Price calls this the correlations without causation view. The correlations in the quantum eraser are features of the four-dimensional quantum state of the entangled pair, which exists as a single structure spanning both temporal endpoints. The signal detection and the idler detection are correlated because they are both aspects of the same four-dimensional quantum state. Neither caused the other. The four-dimensional state caused both. The question that the block universe raises for quantum mechanics is deep. In a block universe, what is the wave function? The wave function is usually thought of as evolving through time, collapsing when measured, updating as events occur. But in a block universe, time does not flow. Events do not occur. Everything is fixed. Some physicists, particularly those working on quantum gravity, argue that the wave function of the universe is timeless. It does not evolve. It is a single mathematical object describing the entire four-dimensional structure. What we experience as temporal evolution is an approximate description that holds good within the block for observers who are themselves processes in time. This timeless wave function picture connects to work by Julian Barber, who has argued that time is not fundamental to physics. In his view, the universe is a collection of instantaneous configurations of all matter, and what we call time is just the ordering relation between those configurations. There is no time. There are only relative configurations. If time is not fundamental, then the arrow of time, the direction of causation, and the temporal ordering of cause and effect are all emergent phenomena, the features of our experience within the universe rather than features of the universe itself. The quantum eraser result in this framework is not about the future changing the past. It is about correlations within a timeless structure that look, from within time, like one event influencing another. This is speculative. These ideas are at the frontier of research, not established physics, but they are consistent with everything the quantum experiments have shown, and they point toward a picture in which the conceptual categories we use to understand the world, time, causation, before, after, are human-scale approximations to something more fundamental. Julian Barber has developed one of the most radical versions of the no-time view in physics. In his book, The End of Time, Barber argues that there is no such thing as time at fundamental level. What we call time is an ordering relation between instantaneous configurations of matter. Each configuration is a complete snapshot of the universe at one moment. The sequence of configurations that we experience as the passage of time is a path through a timeless space of possible configurations, called Platonia. The appearance of time flowing is produced by the structure of the configurations themselves. Each moment contains records of previous moments, memories, and traces that give the illusion of continuity. But the configurations themselves are timeless. They all exist, simultaneously, in Platonia. The universe does not change. It does not evolve. It is a static mathematical structure, and what we experience as the history of the universe is just a particular path through that structure. This is the most extreme version of the block universe idea, applied to the foundations of quantum mechanics and general relativity simultaneously. The practical consequences of quantum non-locality and entanglement are arriving in the world with increasing speed. Quantum cryptography uses the properties of entangled particles and Bell inequality violations to create communication channels that are theoretically immune to eavesdropping. Here is the key property. If you send information using quantum states, any eavesdropper who tries to intercept and copy those states will inevitably disturb them. Quantum mechanics forbids copying an unknown quantum state perfectly. This is the no-cloning theorem, a direct consequence of quantum linearity. Any attempt to copy a quantum message leaves a detectable disturbance. Combined with entanglement and Bell tests, quantum key distribution allows two parties to generate a shared random key that is guaranteed to be secret. If an eavesdropper has intercepted any of the quantum states used to generate the key, the error rate in the correlations will be higher than expected, and the two parties will know they have been compromised before using the key to send any actual message. Quantum cryptographic systems are not theoretical anymore. They are deployed in financial networks, government communications, and research institutions. The Swiss government used a quantum encrypted channel to secure vote counts in 2007. Banks and telecommunications companies operate quantum key distribution networks. The physics that seemed most abstract and most strange is now a working security technology. The reason it works is the same reason the double-slit experiment produces interference patterns. Quantum states are genuinely in superposition until measured, and measuring them changes them. The same property that made quantum mechanics feel weird and counterintuitive is exactly the property that makes quantum cryptography unbreakable. Quantum key distribution has been demonstrated over a variety of platforms, distances. Fiber optic quantum key distribution has been demonstrated over hundreds of kilometers. Satellite-based quantum key distribution has been demonstrated over thousands of kilometers. Ground-based free space quantum key distribution has been demonstrated over tens of kilometers. The main technical challenge is photon loss. Quantum states cannot be amplified in transit without being destroyed, so the quantum channel becomes exponentially lossy with distance. This is solved by satellite-based approaches, which avoid the most lossy part of the crossing through the atmosphere by doing the long-distance part in the near vacuum of space. Quantum repeaters, devices that can extend entanglement over longer distances without amplifying the quantum states, are being developed to address the loss problem for ground-based fiber networks. When quantum repeaters are available at commercial scale, they will enable quantum cryptographic networks spanning the entire globe. Quantum teleportation sounds like science fiction and is routinely misunderstood as beaming matter from one place to another. It is stranger and more interesting than that. It is the perfect transfer of a quantum state from one particle to another, destroying the original in the process. The setup requires 3 particles. Alice has particle 1 in an unknown quantum state she wants to transfer to Bob. Alice and Bob also share a pair of entangled particles, particles 2 and 3. Alice measures her particle and particle 2 together, performing what is called a Bell state measurement. This destroys the quantum state of particle 1 and creates a specific correlation between particles 1 and 2. Alice then sends Bob a classical message, 2 bits of information, describing which of 4 possible outcomes she got. Bob uses that classical message to apply a specific correction to his particle 3. After the correction, particle 3 is in exactly the same state that particle 1 was in before Alice measured it. The state has been teleported. The original was destroyed. The copy appeared at the remote location. No information traveled faster than light. The classical message that Bob needed to complete the teleportation traveled at the speed of light or below. The entanglement enabled the transfer of the quantum state, but the classical channel was essential. Without it, Bob's particle 3 contains no usable information. Quantum teleportation does not violate special relativity. What it does demonstrate is that quantum information, the quantum state of a particle, is not tied to any particular location. It can be disembodied from the physical particle that initially held it and instantiated in a different particle at a different location. The quantum state is more fundamental than the physical object. Quantum teleportation was first demonstrated by Anton Zeilinger's group in Vienna in 1997. By 2017, a Chinese team had teleported quantum states over 1,400 kilometers using a satellite. The quantum state of a photon in one location was transferred to a photon in a location more than 1,000 kilometers away. The entanglement used to do it was maintained over that distance. This is one of the most remarkable experimental achievements in modern physics. The Chinese satellite Misius launched in 2016, has been a platform for multiple landmark quantum experiments. In addition to the 1,400-kilometer quantum teleportation demonstration in 2017, MISSIUS has been used for satellite-based quantum key distribution, demonstrating secure quantum communication between ground stations in China and Austria, and for tests of Bell inequality violations over intercontinental distances. The satellite carries a source of entangled photon pairs that can distribute one photon to each of two widely separated ground stations. The ground stations measure the photon polarizations and can test Bell inequalities using the satellite-distributed entanglement. Bell inequalities were violated over the satellite link, confirming that quantum entanglement is maintained over a distance of more than 1,000 kilometers through space. These experiments demonstrate that quantum networks operating at global scale are technically feasible, and that the quantum correlations that the Bell tests measured in small laboratory experiments survive at distances spanning continents. Quantum computing takes the superposition principle and turns it into raw computational power. A classical computer processes bits, each of which is either 0 or 1 at any given moment. A quantum computer processes qubits, quantum bits that can be in a superposition of 0 and 1 simultaneously. The computational implications are staggering. Imagine you have 10 qubits. Each qubit is in a superposition of 0 and 1. The full quantum state of 10 qubits simultaneously encodes all 1,024 possible combinations of 10 classical bits. When the quantum computer performs an operation, it applies that operation to all 1,024 states at once. With 50 qubits, you have over 1,000 trillion states. With 100 qubits, you have more states than there are atoms in the observable universe. This is not theoretical. Quantum computers exist. IBM, Google, IonQ, and others operate quantum computers with dozens to hundreds of qubits. In 2019, Google's quantum processor performed a specific mathematical task in 200 seconds that would have taken a classical supercomputer, according to their estimate, 10,000 years. The claim was disputed in detail, but not in principle. Quantum computers can do things that classical computers cannot. The reason quantum computing works is the same reason the double-slit experiment shows interference. Superposition is real. The quantum computer is genuinely processing all those states simultaneously, not one at a time. The interference between different computational paths amplifies the correct answer and suppresses incorrect ones, allowing the final measurement to extract the right result with high probability. Quantum computers are hard to build and hard to keep coherent. The same interactions with the environment that cause decoherence in large molecules that destroy quantum interference also corrupt qubit states. Keeping qubits quantum requires extreme isolation, near absolute zero temperatures, vacuum chambers, electromagnetic shielding. The engineering is extraordinary, but it works. And the fact that it works is direct experimental evidence that quantum superposition is physically real, not a mathematical convenience. The computational power of quantum computers comes from processing real, physically existing superpositions of states. Each qubit is really in two states at once. The parallel computation really happens. The threshold for quantum computational advantage, the point at which a quantum computer can solve a problem that a classical computer cannot solve in a reasonable time, is an active area of research. Google's 2019 claim of quantum advantage for a specific sampling problem was disputed by IBM, who argued that improved classical algorithms could match the quantum result. This debate is healthy. It pushes both quantum computing and classical computing to improve. The currently accepted position is that quantum computers do have genuine advantages for specific types of problems, including simulation of quantum systems, factoring large numbers via Shor's algorithm, searching unstructured databases via Grover's algorithm, and certain optimization problems. For these problems, the quantum speedup is provable, not merely conjectured. For general classical computing tasks, Quantum computers offer no advantage. The art of quantum algorithm design is finding the specific problems for which quantum interference and entanglement provide a genuine computational benefit. Everything covered so far points toward a picture of reality that is fundamentally different from what everyday experience suggests. Take the key results in sequence. Quantum systems exist in genuine superpositions until measured. Measurement collapses the superposition, but the mechanism of collapse is unknown and may not be a physical process at all. The availability of information determines quantum behavior in ways that go beyond physical forces. The choice of measurement setting can determine the behavior of a particle retroactively. Erasing information can restore interference in data that was already collected. The correlations between entangled particles cannot be explained by any local mechanism. The future influences the present in quantum systems that are post-selected on specific outcomes. The boundary between quantum and classical behavior has not been found by experiment. Put all of this together, and the world looks very different from the one you started with. The universe is not made of objects at definite locations with definite properties. At the quantum level, objects have no definite properties until measured. The measurement creates the property rather than discovering it. This is not a limitation of our instruments. The property does not exist before the measurement. There is no deeper layer of hidden variables where it already exists. The universe is not strictly causal in the classical sense. The correlation between a past event and a future event can run in both temporal directions simultaneously. The future can influence the past, not in a way that allows you to send a message back in time, but in a way that affects the statistics of measurements in ways that are experimentally confirmed. The quantum eraser is the clearest demonstration of this. The experiments of Aharonov and colleagues on weak values are another, time, at the fundamental level, may not have the directional structure we experience. The laws of physics are time-symmetric. The second law of thermodynamics gives time a statistical direction. The block universe picture says past and future are equally real. The two-state vector formalism says both temporal boundaries contribute to the present quantum state. The synthesis of quantum mechanics and relativity, at the level of quantum field theory, does not resolve the foundational questions. Quantum field theory is the most precise physical theory ever constructed, capable of predicting the magnetic moment of the electron to 11 decimal places. But it does not explain wave function collapse. It does not resolve the measurement problem. It does not choose between the interpretations. Quantum field theory is quantum mechanics applied to fields rather than particles, and all the foundational puzzles of quantum mechanics remain puzzles in quantum field theory. The combination of relativity and quantum mechanics that physicists use to calculate everything from the Higgs boson to the fine structure of atoms is operationally complete and philosophically mysterious, just like quantum mechanics itself. The mysterious parts are the same parts. They did not go away when the theory was made relativistic. Some physicists argue that a fully retrocausal formulation of quantum mechanics would be an improvement on the current situation. The current situation involves non-locality, which is strange and uncomfortable. Instant influences across any distance, undetectable but real, violate the spirit of everything special relativity achieved. If retrocausality could replace non-locality, if the correlations between entangled particles could be understood as a consequence of both particles being influenced by their shared future rather than by each other's present state, then the faster-than-light issue would dissolve. The trade is one kind of weirdness for another. Retrocausality violates our intuition about the direction of time. Non-locality violates our intuition about the structure of space. They are different violations, and some physicists find the retrocausal violation more geometrically natural, more in keeping with the block universe picture, less damaging to the overall structure of physics. A retrocausal theory of quantum mechanics would be time-symmetric. Influences from past boundary conditions and future boundary conditions would both contribute to present events. The correlations in Bell tests would be explained without any signal traveling between the particles. The correlations arise because both particles, at the moment of measurement, are influenced by the same shared quantum state, which carries information about both the past preparation and the future measurements. This is not an established theory. It is a research program, incomplete, with active debates about whether a full retrocausal quantum mechanics can be constructed that reproduces all experimental predictions while eliminating non-locality. The Aharonov school has made the most progress. The transactional interpretation of Kramer makes the retrocausal picture concrete, if not widely accepted. But the research program exists. The mathematical tools exist. The experimental evidence, the quantum eraser, the delayed choice result, the anomalous weak values, points in this direction, and it is possible that the next major development in quantum foundations will be a fully time-symmetric formulation of quantum mechanics that makes the retrocausal structure explicit. The retrocausality research program has been developed by a small but serious community of physicists and philosophers, including Hugh Price, Ken Wharton, Matthew Leifer, and others. This community has argued that a time-symmetric formulation of quantum mechanics would be possible and natural, and that the apparent weirdness of quantum mechanics, including the Bell correlations and the quantum eraser, is a consequence of artificially imposing time asymmetry on a fundamentally time-symmetric physics. Their work has produced specific mathematical proposals for retrocausal quantum theories, though none has yet been completed into a full theory that reproduces all quantum predictions. The main technical obstacle is making the retrocausal influences consistent with the known causal structure of spacetime. How do future measurement settings influence past quantum states without sending information backward in time? Working out the details is an active research problem. The community is small, but the publications are in mainstream physics journals, and the arguments are taken seriously by Foundation's researchers. Step back from the technical details and look at the full picture that has emerged from a century of quantum experiments. The universe you live in is not the universe you thought you lived in. Objects do not have definite properties before measurement. The electron has no position before you look for it. The photon has no path before you record it. These are not statements about the limits of human knowledge. They are statements about the nature of physical reality, confirmed by the most precise experiments ever performed. Observation creates facts, rather than discovering them. When you measure a quantum system, you bring a fact into being. The same act that reveals a property also creates it. Before the measurement, the property was genuinely absent. After the measurement, it genuinely exists. This is not metaphysics. This is the operational content of quantum mechanics. The past is not fixed before the present acts. The delayed choice experiment shows this concretely. A choice made now determines what a photon was doing moments ago. At the cosmic scale, choices made today may participate in determining what photons were doing billions of years ago. The past is not a completed story that the present inherits. The present contributes to writing the past. The future influences the present. Quantum correlations connect events across time as well as across space. The Kim experiment shows that a future measurement on an idler photon determines patterns hidden in signal photon data that was already collected. Aharonov's weak values show that future post-selections contribute to present measurement results. The two-state vector formalism makes this precise and quantitative. Entanglement connects things across any distance and any time without any classical mechanism. Bell's theorem proves no local hidden variable theory can explain the correlations. The universe is either non-local or non-real. The experiments have ruled out every middle ground. All of this is confirmed by experiment, not suggested by theory, confirmed by data. The universe is strange in these specific, quantifiable, testable ways. And the technologies built on that strangeness, quantum computers, quantum cryptography, quantum teleportation, work. The double-slit experiment is sometimes described as the central mystery of quantum mechanics, the one experiment that captures everything that is strange about the quantum world in the simplest possible form. Richard Feynman said this explicitly. He said, "If you could understand the double-slit experiment, you would understand all the mysteries of quantum mechanics." He did not mean the experiment is easy to understand. He meant that all the mysteries converge on it: the superposition principle, the measurement problem, wave-particle duality, the role of information, the relationship between observation and reality. All of them are present in the simple setup of two holes, a stream of particles, and a screen. Every experiment described in this account, the delayed choice experiment, the quantum eraser, the Bell tests, the Aharonov weak values, the quantum Zeno effect, is a development of the same mystery, a probe of the same underlying strangeness, a different angle on the same impenetrable wall. The wall has not fallen, but the picture of what is behind it has become, if not clearer, at least more precisely strange. Come back to the beginning. A particle is fired at a wall with two holes. It crosses the gap alone, in silence, with no one watching. What is happening in that crossing? Quantum mechanics has a precise answer. The particle exists in a superposition of paths. It has no definite trajectory. It is not taking one path secretly, in a way we could find out if we tried. It genuinely has no path. The mathematical description of its state is a spread-out wave of probability that passes through both holes simultaneously. That wave interferes with itself on the other side. The particle lands in a pattern that reflects that interference. For a century, physicists have been asking what this means. What is the particle actually doing in the dark gap between the source and the screen? Is it everywhere at once? Is it nowhere? Does the question have an answer? Copenhagen says the question is meaningless. Before measurement, there is no fact about the particle's position. Asking where it is before you look is like asking the precise location of a dream. Many worlds says every possible path is taken in different branches of the universe, all of them real. Pilot wave says the particle has a definite position and takes a definite path, guided by a wave we cannot directly observe. Relational quantum mechanics says the question only has an answer relative to a specific observer, and different observers can have different answers. None of these interpretations is experimentally preferred. All of them reproduce the same predictions. All of them must accommodate the same experiments: the double slit, the quantum eraser, the delayed choice, the Bell tests, the cosmic quasar delayed choice, the weak values of Aharonov, the quantum Zeno effect, the loophole-free Bell violations, the molecular interference results. All of them are reaching for the same thing, a picture of what the world is, underneath the measurements, and none of them has reached it, not cleanly, not without cost. The particle crosses the gap. The detectors on the other side of the universe, built in 1999 and 2007 and 2015 and 2017, have all recorded their results. The data exists. The patterns are there, waiting in the statistics. And at the level of what is actually happening in that dark crossing, physics has been honest enough to say, we do not know. A century of work, the most precise theories in the history of science, Nobel Prizes, satellites, quantum computers, encryption that governments use to protect their secrets, and at the core of it all, a particle crossing a dark gap, and the honest admission that no one knows what it is doing when no one is looking. That admission is not a failure. It is the most accurate statement physics has ever made about the world. The universe, at its most fundamental level, does not have a definite story until someone asks for one. And the moment you ask, something extraordinary happens. A fact comes into being. A particle appears. A record is made. And you are left with the question that will keep physics busy for the next century. What exactly was there before the asking? Every physicist who has confronted these results honestly has had to revise what they thought the universe was. The revision is not of a small detail, but of the deepest assumption that the world has a definite, independent existence outside of observation. The experiments answered this assumption with extraordinary clarity. They answered it with data. The question of what is happening when no one is looking is the oldest question in quantum mechanics and maybe the deepest question in all of science. It asks about the relationship between the physical world and the observers who investigate it. It asks whether the world has an objective existence independent of observation or whether it is, in some fundamental sense, constituted by observation. It asks whether the classical picture of a universe that simply is, regardless of whether anyone is watching, is correct, or whether the quantum evidence requires a more participatory picture in which observation and reality are intertwined at the deepest level. These questions are not settled. The experiments have ruled out the simplest classical pictures. They have confirmed the quantum ones, but the quantum pictures come in multiple versions, each with different implications for the nature of reality, and the experiments have not yet chosen between them. The question remains open. The particle is still crossing the dark gap. The screen is still waiting, and the universe is not saying.